Hi everyone. In this video, we're going to continue looking at probability, but we're going to think about what outcomes can happen with certain events. So I want you to take a moment to think about what it means to be independent of something rather than dependent of something. Because we're going to look at different events today that could be independent of each other, or maybe they might have some kind of effect on one another. So let's look at these two examples here, starting with A. A person pulls a red marble out of a bag that has 5 blue and 7 red marbles and does not replace it. Then a person pulls another red marble. Is the probability of pulling the second red marble out dependent on pulling the first red marble? So here's a visual of what this bag could look like. We have 5 blue, 7 red. So if I were to pick one and it happened to be red, the probability of that happening is 7 out of the total amount of 12. Now, the one that I picked is now gone. So I'm going to look at a different bag. Now the probability of me pulling a red marble is changed to 6 out of 11. So if I were to calculate these two, 7 out of 12 and 6 out of 11 are definitely not equal to each other. So in this case, because we didn't replace, so the big reason here is not replacing that marble, it changed the outcome of the second probability. So when that happened, the second event depended on the first one, right? This also would have changed if we pulled a blue marble or something different happened. So my second probability depended directly on what happened in the first scenario. So this would be an example of a dependent event, really because of that no replacement. Now, if that red marble went right back in and you just kept pulling from the bag, then it would go to independent because you're going to put back to have the same total you started with. The odds are still the same. Now, if I go over at B, we have a person who's flipping a coin and notes that it comes up as heads. Then the person rolls a standard 6-sided die and notes that it comes up as a number less than 3. Is the probability that the number came up less than 3 dependent on getting a heads when flipping the coin? Well, no. In this case, you can flip a coin as many times as you'd like. No matter what, it's going to be 1 out of 2 for getting a heads because you can either get heads or tails. No matter how many times you flip that coin, those are your only two options. So it's a 50-50 shot, right? So it's 50%, 0.5, or 1/2. When I roll this die here, they're two totally separate things. Now, in part A, it was the same bag that was affected, but you have part B here has a coin and a die. Those are totally unrelated. No matter what, however many times I roll this die, it's still going to be 2 out of 6 for me to potentially get a number less than 3 because it's only the options of 1 and 2 out of 6 numbers altogether. So no matter what I do with the coin or the dice, they're still going to have those same odds. So basically, independent means there's no effect on the outcome of the event. So no matter what, for flipping a coin and rolling a dice, they are independent of each other because no matter what happens with those two individual events, they have no effect on one another. Okay? Dependent is something that would change the outcome. So let's get a little bit more formal of a definition here of independence. So we have a spinner to the right here. We're going to spin it once and we want to take the outcome. Now let E be the event of getting an even number, let P of R be the event of getting a prime number, and let L be the event of getting a number less than 5. Find the following probabilities. So first we're just going to get the probability of E, of getting an even number. So it's 2, 4, 6, and 8. So it's 4 out of the total possibilities of 8 because I could have spun anything on there. So it simplifies to 1/2. Okay, that can also be known as 0.5 or 50%, any way you want to record that. Now in the next one, however, we have the probability of getting an even number given that the outcome was a prime number. So remember, given means there's a restriction here. So we know for sure when you see given, that's that line, that it was a prime number. So I have 2, 3, 5, and 7 that are my potential primes. So there's 4 potential prime numbers I could have picked. And the only even one that's out of those is 2 So that means there was only one possible even number I could pick out of the primes. So that changes my probability to 1/4. And again, you could do 0.25, 25%, any of those are acceptable. Now, if I keep going with that idea here, if I want the probability of getting an even number given the outcome was less than 5, so less than 5, I'm looking at 1, 2, 3, or 4. So there's 4 potential numbers that are less than 5, and out of those, there were 2 numbers that were even. But 2 out of 4 simplifies back to that 1/2, or the 0.5, 50%. So that being said, when I look at D here, which event does E depend on? Prime or less than 5? And how can you tell? So in this case, when I'm looking here, my probability of getting an even number was 1/2, because there was 8 total, half of them were even. Now, notice in part C, when I did less than 5, it didn't change my probability at all. I have 1/2 and 1/2, because basically I'm just cutting out the second half of this board, so it's really not going to change my probability at all. Because there's no change in those events, those two are independent of each other. It did not change my probability. But in the other case of this particular problem, B, we got 1/4 instead of 1/2. So which event does E depend on? In this case, it depends on it being prime. And the reason we know is because the outcome changed. Okay, so we started as being even, as 1/2, but when you put that restriction, it changed it. So there was dependence there. But if we wanted to find a formula to see if something's independent, well, here, notice for A and C, the probability of being even and the probability of getting an even given the probability of less than 5, since those two are the same, what the probability here is, if I have a probability of A given B, it's independent if I still get the same probability as A by itself. And that works too if I change this up and we wrote it as probability of B given A, it would still be equal to the probability of B. Basically, the big idea here is if you have a restriction, a given, and it doesn't change the probability of the original, then it's independent. Okay? But something that I don't necessarily love that the Regents words this as is depends on. Now, usually they will use questions that could show dependence, but sometimes we can't really show dependence. And I'm going to explain that a little bit more in question 2 here. So manatees are an endangered species of herbivorous aquatic mammals found primarily in the rivers of Florida. In a recent study, the probability of a manatee dying due to a collision with a watercraft was 0.27. Meanwhile, at a local high school, it was found that the probability of a student eating ice cream was 0.62. The probability of both events happening is 0.14. Are these two events independent of each other? Now, I'm going to draw us a Venn diagram just to help our ideas for a moment. So this first circle will end up being our manatees dying. And our second circle will be the probability of a student eating ice cream. And remember, we put that all in a box together. So the probability of both happening, that's where I would start, is this 0.14. So that goes in the middle. Now remember, the whole circle is the manatees dying. So that should add up to a total of 0.27 or 27%. So I'm going to subtract that 0.14 to get 0.13. And same thing with the ice cream, we're looking at 0.62, subtract 0.14 to get 0.48. And then the event of neither happening, well, I'd add those three up together, we would have 0.75. So there's a 25% chance that neither could happen. Now, let's look at this in terms of what we're dealing with now. So we would have the probability of, let's say, a manatee given a student eating ice cream. So the manatee dying if a student eats ice cream. They're independent if it's the same for the manatee to die either way. So remember, with this given, we know ice cream's happening, right? So we know ice cream's happening because that's what the given is. But then manatees dying also happens. So that's 0.14. And it's equal to the probability of a manatee dying. So that's 0.27. So these two events do not equal each other. Now I want you to ask yourself, every time you have ice cream, does a manatee die by colliding into a boat? No, right? That's a little bit crazy to think about. So even though these events aren't independent of each other, I wouldn't necessarily be okay saying they're dependent, like a manatee dies because you eat ice cream. No. So I'd prefer that you said not independent of each other. Okay? Because I want you to keep in mind, there's probably other factors that could have happened, right? Think about when people are on their boats more and when students eat ice cream more, right? The weather is warmer. Maybe it's summertime. But let's not jump ahead and say that because we had ice cream, manatees are going to die. I want it to be safe to eat my ice cream, okay? So as far as the Regents goes, they'll probably give you a question that dependence makes more sense. So if you wrote dependent, it would still be counted as full credit. But I just wanted you to understand that it's not necessarily dependent of one another, okay? You're not forcing that to happen in this case. But they don't really get into those specifics on the Regents, and I just wanted you to be aware of that. So let's look at one more question. So we have a survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. Does it appear, based on the data in this table, that the preference for math as a favorite subject has dependence on a student's gender? Show the analysis and explain your findings. In this case, we're trying to see if the preference for math as a favorite subject has dependence on a student's gender. So those are two things we're looking at. So we can say math, the probability of math being the favorite given the gender would still be equal to the probability of math. So this is the same as saying math and the gender, right? That's essentially what we're still saying. Now you can use either gender in this case since there's two of them. So it's your call. I'm going to use female. And if you did male, that's totally fine. But so I'm saying that we know that they're female. So it's out of a total of 30. And the ones that are math favorite is 8. And if it's independent, it will be equal to everyone that favored math. So 18 out of the total here, 57. Okay. And then I just plug those into my calculator because I don't have to know off the top of my head if they are equal. But 8 divided by 30 gets us 0.2666 repeating. Eventually get that 7. And if I do 18 divided by 57, we get 0.31578,947. Either way, definitely not equal, so not independent. So in this case, you can say it's dependent because of the way the question's worded. Either way, not independent or dependent would get you full credit. And again, if you did this again for males instead, it would show you not equal, and still we can go with that dependence idea. I jumped ahead a little bit here on the next one for us just because I'm getting close to the end of my video. But the probability of social studies given gender again. So this time I switched up to male, but that's 9 out of 27. And the probability of social studies being a favorite by itself is 19 out of 57. they both equal 0.3 repeating, this is a case of independent.